Hey, good morning again. This is the last part of the recording. This video part 3 will cover the basic rules of the first order derivative. I will go over one more time what the basic rules are, and then one by one I will show examples of the basic rules of the first order derivatives. Before I start, in order for all of you to follow with directions and where to find things, even though they're being posted in Brightspace, let me share with you. So what I'm sharing is the screen. This is the site on Brightspace 251, and then you have limit at infinity, the video link recording part 2. You have an email for the midterm exam review notifying you that the copy of the midterm exam is posted. You go to Brightspace content, you look at the midterm exam review to access the file. So you go Brightspace content, and there's a module created for the midterm exam, and then you have the review. Okay? So you can download the file by clicking on the arrow sign and then the option download. Going back to the announcement, at the same time, you have the video recording part 1. This is mainly focused on the limits and then adding more information about limits, especially one case of the limit at infinity. This is part 2, adding again more information about limits, focusing on limit at infinity, part number 2. And now I will stop sharing this and then transition into the file. And that's going to be basic rules of the first order derivative. So let me access the file. Once I finish going over this, the file will be posted, and this one has information of recording part 1 and recording part 2. So what are the basic rules? I'm going to go over the basic rules of the first order derivative. You see some of them highlighted. The derivative of, let me make a correction on this one, I guess. I would like to use the precise notation with the square bracket. The derivative of trigonometric function sine of x. So prime notation means the derivative is cosine. And then correcting the notation, the derivative of cosine of x is negative sine. Exponential functions, the derivative of e to the power x notation of the derivative is e to the power x, and then again correcting the notation of the derivative of ln of x is 1 over x. I'm gonna add a couple more derivatives. So I'm gonna transition to the famous rule known as the power rule of the first order derivative. So we are differentiating x to the power n, and there will be some special scenarios that I would like to discuss with you. So this is exponent n in front of it, multiplied by x to the power n minus 1. And then in that particular group, as I mentioned, I would like to discuss a couple of special derivatives, such as x to the power 2 derivative. So exponent is 2 in this case, so you're going to bring 2 in front of it. You're going to multiply this by x to the power 2 minus 1, so you reduce the exponent by 1. So altogether this is, so let me add an additional step. This is 2 times x to the power 1. And this is why this is a special case. So it's going to be 2x, because x to the power 1 is just x. So this is one special case. Try to remember this. It's going to show up later on as special cases of the power rule. There's another special case that I'm about to discuss. So I'm going to copy and paste this one and then make adjustment and show you the other special case. And that's the case of exponent being 1. So if the exponent is 1, then you multiply 1 by x to the power 1 minus 1. And then x to the power 1 minus 1 becomes x to the power 0. And x to the power 0 is 1. Any finite number raised to the power 0 is 1. So altogether, this is 2. So reminding everyone, any finite number raised to the power 0 is equal to 1. So these are two special cases. I'm going to go ahead and save this. Well, let me check and see if this is saved correctly into the folder. Here's the folder. Is the spring correct folder? There you go. Okay. So these are basic rules of differentiation. The other rules that I mentioned, we have a rule that allows you to have the summation of two functions. So let's call them f of x plus g of x. And you differentiate them. This is widely applied when you have a polynomial, multiple terms. So you're allowed to distribute the derivative. So you can write this as f prime of the variable x plus g prime of the variable x. Now we can mimic this particular rule for the difference between the two functions, but the sum and the difference, so this is summation. So this is the derivative of the sum of two functions. And then once again, I'm going to copy and paste this underneath and call this the derivative of the difference of two functions. In both scenarios, you notice that you notice that derivative can be distributed. But that's not the case when you're multiplying and dividing. So here's the case of multiplication. I'm going to use the correct notation. This is f times g prime. And then, of course, let's do this u times v. I like to do it with two scenarios because there are some cases where it is needed for you to use u and v rather than f and g because the notation f of x will be used for the entire product. And then I'll show you exactly what I'm referring to. And then once again, that's going to be the case for u divided. We call this the quotient case. And let's do the same thing for f and g. Quotient case, so f divided by g. And the reason why I'm using both forms, because as I mentioned, there are cases where f is used as a notation, f of x for the entire function. We highlight this in blue as it is, okay? Continue to save this. Some other basic rules of integration, coefficient and constant rule. So if you have coefficient k multiplied by the function f of x, and this is differentiated, you can take the coefficient k outside the derivative notation, and you simply multiply this by the derivative of f of x, which is f prime of x. And then finally, we have that constant rule where c is the constant and you're differentiating, that's going to be equal to 0. So C represents a constant. In the previous case, K represents a coefficient. Okay? So you have all the solutions. So now let's try to use them. I'm going to start with part A. And let's pull part A. This is the list of examples, long list of examples. And then let's find out how that's going to work. Okay. So basic rules of the derivatives. I'm going to make this bigger. And then, of course, there you go. And I'm going to grab the first one. The first one is the function f of x equals x to the power 8. Let me eliminate this. I don't know if formatting is a bit weird. There you go. Okay, now it's better. So this is A, part A. We have a function f of x that is given as x to the power 8. Our goal is to find the derivative. So to find the derivative, find f prime of x using power rule. So I'm about to use power rule. So what is power rule? And what the power rule is saying, here's the power rule right there. So what the power rule is saying, I'm going to copy to make it easier for you to follow through. Here's the power rule. So what the power rule is saying is, in order to differentiate x to the power 8, according to the power rule, you have to bring the exponent 8 in front of it, and then multiply this exponent by x to the power 8 minus 1. So the current exponent, just bring it in front of the variable x as a coefficient, and then decrease that exponent by 1, and then simplify. So that becomes 8 multiplied by x to the power 7, and that's it. And that's going to be the final answer for part A. Okay. So now I'm going to transition. I have to save this. There you go. I'm going to transition to part B. Now, why is this interesting? Let's find out. The way this design is interesting has a variable in the denominator. There you go. So this is part B. So in order for me to find f prime of x using the power rule, I must write the exponent must change exponent into a negative exponent. So I have to take this. This requires your algebraic skills. You have an exponent in the denominator, so that becomes your x to the power -6. Without changing this into a negative exponent, you're not going to be able to use the power rule. And now I'm ready to use the power rule the same way I used it for part A, but now I have a negative exponent. But it's still okay. The rule must be applied this in a very similar way. So your coefficient is going to be -6. That's the number that represents the exponent. But be very careful with your algebraic operation. Now you have variable x. The current exponent is -6. You have to subtract 1 because you always decrease by 1. Again, very careful with your operations. So -6 times x, that's to the power -7. You cannot keep this as the final solution. Why? Because of the negative exponent. The negative exponent must be changed into a positive by placing the exponent back into the denominator. So that's going to be 1 over x to the power 7. Now the exponent is changed into positive. Am I finished? Again, you're not. I need two fraction forms. One to write -6 as a fraction over 1 to create an opportunity for myself to correctly multiply these two fraction forms. And the other one is going to be the second fraction form that you see it in there, which is 1 over x to the power 7. Once they both are in the fraction form, it's easy for you to multiply. -6 times 1, that's -6. And then x to the power 7 times 1, that's going to be x to the power 7. And that should be the final. So a bit different from the previous one, the way this is designed. Okay, now we have part C. Let's see what is in part C. Part C, we have a function that is given as the sum of two terms. Interesting. This is going to require that summation rule of the first order derivative. Let's see how that's going to apply. So let me remind you what that summation rule of the first order is. Okay. Now, before I start, here's the focus on the summation of two functions. So when you differentiate, you're allowed to distribute the derivatives. And that's what I'm going to do. So I'm going to start by the distribution of the two derivatives. Here's the function. So in order for me to find f prime of x, I'm going to differentiate x to the power 5 plus, and then I'm differentiating 6x squared. So that's the distribution of the derivative. Okay? And now I look at them individually. So x to the power 5 requires the power rule of the first order derivative. So for now, I'm going to keep this as it is, but I kind of like know exactly what I'm doing in terms of the rules that I'm using. The only thing I'm going to do is I will apply a basic rule of differentiation known as the constant rule, known as the coefficient rule, because I notice that I have a number 6 in front of the variable x to the power second. So that means I have a coefficient 6, which I take it out. We do not differentiate coefficients. So you notice that is taken out. And now for each one of them, I have to apply the basic rule of differentiation known as the power rule. So starting with the first one, 5 in front of the variable x, then x has to be multiplied by power 5 minus 1. So you notice the power is decreased by 1 plus. Second term, I already have a 6 in front of it, but the exponent of the function x squared is 2, so will be another 2 as a coefficient in front of it. That will be multiplied by x to the power 2 minus 1. So both exponents are decreased by 1. So the first one is a 5 x to the power 4, because 5 minus 1 is 4, plus 6 times 2 is 12. So we have a coefficient that is computed by multiplying those two coefficients. And then x will be to the power 1. But remember, I started off by showing you two special cases of the basic rules. And I can even highlight them. Makes sense if I do that in green. So you see, if I have x to the power 1, that's just x. We do not write the exponent. And that's what I'm dealing with. So I have an x to the power 1. Which I can write is simply as an x. And that's it. That's the final solution for part C. There you go. So we are working with part D. Part D, let me move this into the next page. Function is 6x squared minus 6 cosine of x. Again, it's a two-scenario application. So we are differentiating using the rule known as the rule for the difference between the two functions. So you're allowed to distribute the derivative. If you have f of x minus g of x differentiated, that's going to be f prime of x minus g prime of x. So let's go back. There you go. And then we are differentiating those two individually. So differentiating 6x squared, differentiating 6 cosine of x. Both terms have a coefficient 6. So notice that the coefficient 6 is pulled out. And then now x squared is differentiated and cosine of x is differentiated. Be very careful. I already differentiated x squared right there. So the derivative is 2x. But you do have the work one more time in details going over. So you have the coefficient 6 multiplied by the exponent 2. So you bring the exponent in front of it. And then x becomes to the power 2 minus 1. Again, minus coefficient 6, and you differentiate in cosine of x. What is the derivative of cosine of x? According to the basic rule, derivative of cosine of x is negative sine of x. And that's why you see negative sine of x. And now you have to simplify. 6 times 2 is 12. X to the power 1 is x. A negative times a negative becomes a positive, and 6 times sine of x is 6 sine of x. That's it. That's the derivative. That is the solution of part D. Now let's get to part F. So I'm going to highlight this. And then, of course, save it. And now let's go to part F. Part F, it's going to require to differentiate a ratio. Now we'll be simplifying this ratio first. And then at the same time, having the opportunity to use the basic rules. So here's the function f of x, x to the third minus 5 over x squared. Now, one way of doing it is you can directly simplify the ratio, and I encourage you to do that. So if I say simplify, you can do something like this. That's not the approach I'm going to take, but I'm challenging you to use that approach. This is an algebraic approach. So I'm going to show you the way you simplify. So you notice that I'm separating the two terms of the numerator, writing this as x to the third over x squared minus 5 over x squared. So you can do that as long as you keep the denominator the same. And then when you look at x to the third over x squared, anytime you divide powers, this is again, as you notice, I'm using a lot of algebra. So it's your opportunity. If you're still having issues, go back and review the properties of powers, algebraic operations, all that stuff. This is one property of exponents. When you divide powers, sharing the same base, keep the base as it is, subtract the exponent. So that's going to be x to the power 3 minus 2 minus. Now, on the other hand, I have a 5 over x to the second. I can write this as coefficient 5 times 1 over x to the second. And then there's a reason why I'm doing it, because I'm about to change this into a negative exponent. And the reason why you're changing it into a negative exponent, because that's going to be the way you differentiate. So altogether, you're differentiating an algebraic expression that look like this: derivative of x minus 5 times x to the power negative 2. For the second one, you have to use the power rule. The variable x, you have to use the power rule. But what I did is you have to write x as x to the power 1. So x and x to the power 1 is the same thing. So you're differentiating x, but when you're differentiating x, is the same as differentiating x to the power 1. So you have this derivative already completed. All you have to do is look at it. It's a special case of the power rule. And the other one is a negative exponent derivative, which was done in part B. So you have a negative exponent example. And once you complete it, you should be able to get the outcome. And then I really like you to take that approach. On my end, I'm using a different approach. I'm treating this as a ratio, and then I'm using the approach of U over V. So here's the approach that I'm going to use. I highlighting one of the functions to be the function U, and then the other function to be the function V. Now, the other thing that you notice is f of x is used for the entire ratio, represents the entire ratio. So there's no way I can use this form of the power of the quotient rule, which is f over g, because f of x represents my entire ratio in this case. So that's why u over v will be the ideal option. Now I can use this option of the first order derivative as long as I successfully identify my function u and my function v. So the top function is going to be my function u, which is x to the third minus 5. So if I have to find u prime, I have to differentiate this function, which means differentiate x to the third, differentiate 5. X to the third is differentiated by using the power rule. So it's 3x to the second. Because you bring 3 in front of it, you decrease the exponent by 1. Now, when it comes to 5, that's a constant. That's the derivative of a constant c, which is 0. So altogether, the top is 3x squared. Now the bottom is x squared. The derivative of it, for the same reason as the power rule, is 2x. You do have an explicit form of differentiation of x to the second in detail. So all you have to do is look at it. And now I'm going to use the quotient rule of the first order derivative. So here's the quotient rule. U prime, which is 3x to the second, times v, which is x squared, minus u, function u is x to the third minus 5, times the function v prime, which is 2x, all over v squared. So the function v is x squared, I have to square it again. Again, property of powers, when you square into another exponent, you multiply the exponent. So that's why the denominator becomes 3x to the fourth. Now, when it comes to the top, you have to simplify. So 3x squared times x squared is 3x to the fourth. And then I have to distribute 2x, but not only distributing 2x, distributing negative 2x. So if I distribute negative 2x over x to the third minus 5, then I have negative 2x times x to the third becomes negative 2x to the fourth. And to negative 5 times the negative 2x, there's two negatives that are multiplied together, so that's 10x. I see two like terms, 3x to the fourth minus 2x to the fourth, that's x to the fourth, plus 10x over x to the fourth. And then one common error, once students see something like this, they notice that there's an x to the fourth at the top, x to the fourth at the bottom. And then they think, oh, that's a common factor, so I can get rid of it. You won't be able to, because x to the fourth, it's a common term, not a factor. Factor means you must have a multiplication present in order to get rid of it. You don't. X to the fourth is it's not alone, has a plus 10x at the top. So because of that particular reason, you cannot get rid of it. But what you can do is you can create a product by factoring out something that is a common factor at the top, and that's x. So once I factor out x, I get x outside, which is highlighted in blue, and then inside is x to the third plus 10, because we just factor out an x. And then at the bottom, I have x to the fourth, which stands as x times x times x times x 4 times. So I get rid of one of those x's, and then altogether I get x to the third plus 10 over x to the third. Once again, you're not going to be able to say that this expression that I call it x to the third plus 10 over x to the third can be simplified, because I notice that I have an x to the third in front of it, which I can think of it as a common factor and get rid of it. That's incorrect. That's a common term. X to the third, it's at the top, but there's a plus 10 next to it. That blocks you from simplifying or getting rid of x to the third. That's it. And then this was our part DF. Okay, wonderful. Now let's see what's next. From part F to part G. So let's look at this part G. For part G, we are going to use the product rule. And then once again, you notice that since f of x represents the expression, I won't be able to use the same product rule. Let me go back to the product rule. Here's the product rule. There's two versions. One is for u and v, two functions, the product of two, and the other one uses f and g. Since f of x represents the entire product, I won't be able to use that second form of the product rule, but I'm going to rely on this particular form, which I call it u and v form. All I have to do is identify the u and the v, differentiate them individually, and then apply the rule. My function u is x squared minus 1. And then the derivative of it is going to be the derivative of x squared minus the derivative of 1. The derivative of x squared is 2x, and the derivative of 1 is a constant, is 0, so that's 2x. So if the function u is x squared minus 1, function u prime is going to be 2x. Function v, we differentiate 3x plus 2. So that means we distribute the derivative to the derivative of 3x plus the derivative of 2. Derivative of 2 is 0. Notice the difference between 3 and 2. 2 is alone, no variable. So it's the derivative of a constant. That's why it's 0. 3 is not alone. It's attached to x. It's a coefficient, so you take it out. And you only differentiate x. I encourage you to look at the derivative of x explicitly at the very top when I introduce the power rule. But you see briefly some explanation of the derivative of x. When you differentiate x, is the same as differentiating x to the power 1. X to the power 1 and x are the same. We do not write exponent 1. And then if you differentiate it, you have to bring, according to the power rule, you have to bring the exponent in front of it. So you get 3 times 1. 3 is already in there in front of it. So now you get a brand new coefficient 1 because of the power rule. So you get 3 times 1. And you have to decrease this exponent by 1. So the exponent becomes 1 minus 1. Eventually, that's 3 times 1 is 3. X becomes to the power 0, which we know is 1, and that's 3. So if function v is 3x plus 2, function v prime is going to be 3, which is the corresponding derivative. And now I'm ready to apply the product rule to get f prime of x. So that's going to be 2x times u prime, which is 2x, times v, which is 3x plus 2, plus function v x squared minus 1 times v prime, which is 3. And now the remaining is just doing some algebraic work. Again, your algebraic skills are so important to perform well with the derivatives. In addition to the new rules, without the algebraic skills, this is going to be almost an impossible scenario. So what are the algebraic skills that I need? An excellent distribution of 2x over 3x plus 2. So 2x times 3x. 2 times 3 is 6. X times x is x squared. So that's 6x squared. Be very careful with the signs when you distribute. 2x times 2 is 4x positive. And now I'm distributing 3 over x squared minus 1. So I get 3x squared minus 3. And combine like terms. 6x squared plus 3x squared, 9x squared plus 4x plus 3 minus 3. And that's going to be the final. So f prime of x, let me copy that, equals 9x squared plus 4x minus 3. Okay, so now we'll transition into another function, and that's going to be our function of part h. The rule that we need is the natural log rule. When we differentiate it is 1 over x. So let's find out how this derivative is going to look like. Okay, so now let's look at this. So part h, we have a function Now, it's not defined as f of x, it's defined as y, but we know y and f of x are the same. So reminding you that y equals f of x. So therefore, y prime, which is the notation of the derivative, is the same as f prime of x, okay? For consistency, I'm going to use the y. So I'm not going to change that. And then I'll find the y prime. That's going to be the derivative of the natural log plus x squared. I'm going to go ahead and distribute, which means I differentiate them individually. Starting with the natural log of x, the derivative is 1 over x, and then derivative of x squared, as we know, is 2x. Now, you can stop right there, or you can merge algebraically the way I did it, but that's all up to you. If you want to merge those two elements, and then sometimes this is required, so you have to pay attention to the directions. You have to put 2x over 1 in the fraction form and find the least common denominator, which in this case is x. So that means the first fraction, 1 over x, stays as it is. This one is not calculus 1. This goes back to your algebra skills. So the first one stays as 1 over x. The second one must be multiplied, the top and bottom, by x. So you get 1 over x plus 2x squared over x, which you can write it as 1 plus 2x squared over x. So therefore, your function y prime, and then it's going to be the final step, is equal to is equal to 1 over 1 plus 2x squared over x. And now finally, I'm going to look at finally, I'm going to look at the last one, and the last one is part I. We have a function with 3 elements. Sine of x is going to be part of the derivative, and then e to the power x. Sine of x is, when it is differentiated, is cosine of x. When e to the power x is differentiated, is e to the power x. And then when the variable x is differentiated as x to the power 1. So the derivative is simply, the derivative is simply 1. Okay? Let's look at the last one. So this is part I. Again, the function is defined as y, but as I explained, y and f of x is the same thing. So therefore, I'm going to stick with the y, the way the function is given. But again, y prime and f prime of x are exactly the same. So the function is the summation of 3 terms. You differentiate in the first, which is 2x. This one has a coefficient. You're differentiating e to the power x and sine of x. Let's look at them individually. So the first one is differentiated by taking the coefficient out. Coefficient is 2. That is attached to x, and simply differentiating x. When you differentiate x, that's the same as differentiating x to the power 1. The second one is derivative of e to the power x. The third one is sine of x. Now, x to the power 1 explicitly is done, as included in this video recording and then lecture notes all together. I want you to look at it as part of the basic rules of the first order. I included special cases, one of them x squared, the other one x, which is x to the power 1, and their corresponding derivatives. So please look at them. Here is the explanation one more time. So we take 2 out. Now we differentiate x to the power 1 using the power rule. So that means we bring 1 in front of it. So now you end up with the product of two coefficients, 2 and 1. And the exponent of x becomes 1 minus 1. So that's x to the power 0 case. So that's why you see 2 times 1 is 2 times x to the power 0. Reminding you that x to the power 0 is 1, okay? The second term is e to the power x. When you differentiate it, you get e to the power x. And then the third is the derivative of sine of x. When you differentiate it, you get cosine. Knowing that x to the power 0 is 1, altogether we get 2 plus e to the power x plus cosine of x. And that's the derivative final solution for part I. Now, this particular example that you see in there, it's an application of the first order derivative. Even though it is in the category of the first order, I always think of this as more like an algebra and precalculus application. And then I'm going to explain the reason why. Is the last example of the video recordings and then the lecture notes. Please look at it. Let me start with this particular equation. This equation in precalculus, when you learned about quadratic function, is known as the position function equation. It is a quadratic equation. A couple of explanations. S of t stands for the position function of the time t. T stands for time. It's extremely popular in physics. S of 0 stands for the initial position. So let's say you have an object, you have to pay attention in the language of the application where this object is placed. If it is placed on the ground level, then the position of that function with respect to ground level is 0 because it is on the ground level. But if the object is placed on top of a building, you have to look at how tall is the building to find out what the initial position of the function or of the object is going to be. If the building is going to be like 1,000 feet tall, that's going to be your initial position function, or S0. Another extremely important element of this equation is the V0. The V0 stands for initial velocity. Again, you have to pay attention for the language of the application, meaning I can give you an example. Example of a swimmer diving into the pool from a platform. A platform is placed, let's say, 200 feet above the surface of the water. So that means the initial position is 200 feet. That's S0. And then the swimmer is getting ready to dive, but it is first initially jumping on the platform. So there's a velocity that goes along with that part. And then you have to pay attention what the velocity is at impact, meaning what is the velocity when the swimmer jumps on the platform. That's going to be the initial velocity. So always look at the language of the application. You cannot make up a number for the initial velocity, the initial position. You simply have to pay attention to the content of the application. Pay attention to the reading of the word problem. And then speaking of that reading, I'm going to read and give you the elements one by one. A coin is placed on top of a building that has a height of 1,362 feet tall. So that means the initial position of the silver coin, S0, is going to be 1,362 because it is placed not on the ground level, it's placed on top of the building. And the building stands 1,362 feet above the ground level. This is how tall the building is. So that's the initial position of the building. Now, the silver coin is not moving. The silver coin in this case is the object. It's placed on top of the building and it's not moving. So that means the silver coin is placed in a fixed position. Therefore, the initial velocity, V0, is going to be 0. Now, the equation of the position function is defined, S of t is given as S of t equals. So the position function is S of time t. Find the time for the silver coin to reach the ground level. Or in other words, when the coin reaches the ground level. When the coin reaches the ground level, the position of the coin changes from the top of the building to the ground level. From the top, which is initially 1,362, changes to the ground level, which is 0. So we have S of t becoming 0. V0 is 0, and then S0 is 1,362. Time in this case, t, is an unknown. Time t is unknown. So I'm going to plug in everything into what we know into the position function equations. All the given information into the equation of position function. And then once we plug it in, that's the equation of the position function. So I'm going to highlight this. And start substituting. S of t is 0 because it's the ground level. So these are the elements that I'm substituting, copying them. Okay. Here's what we're substituting into the equation. So S of t is 0, negative 16 t to the second plus 0 times t because v0 is 0 plus 1,362. So we get 0 times t is 0. So the remaining is going to be a quadratic equation using quadratic formula to solve it. Here's the quadratic equation in general, ax squared plus bx plus c. You identify a to be the coefficient in front of x squared, which is the quadratic term. B is the coefficient in front of x, which is the linear term. C is the constant. And once you identify them, you plug them in. This is the quadratic formula. In my case, I don't have a term in the middle. Most zini. No, stop. I have a quadratic equation with no middle term. So the middle term is 0, t. So therefore, b is 0. But I do have a coefficient in front of t squared, which is the variable in my case is not x squared, it's t squared. So which is a, negative 16. And then finally, the constant, the term without the variable is 1,362. So I'm going to plug them in. I'm getting variable t. Variable is t, not x. Negative b, negative 0, plus and minus square root of b squared, 0 squared, minus 4, times a, which is negative 16, times c, 1,362. I'm going to eliminate the 0, and I have plus and minus. This entire product eliminate 0 square, a minus times a minus becomes a plus, and 4 times 16 times 1,362 is 87,168. Divided by the denominator, which is 2 times negative 16, negative 32. I'm going to break this down in two cases. One positive, square root of 87,168 divided by negative 32, that's negative 9.226. And then the other one is negative square root of 87,168 divided by negative 32, which is 9,226 seconds positive. Now notice that this one is highlighted. I'd like to highlight it in blue. I'm sorry. In blue because all the answers for us are in blue. Yes. And then I'm eliminating this one, the first part, because the time cannot be a negative number. And then I conclude that the time required for the silver coin to reach the ground level is 9.226 seconds. Time can only be measured by a positive number or cannot be measured by a negative number. So that's why the other solution is eliminated. And that's all. Okay, I'm going to post this. Continue to read and then reach out in case. Let me save this as, I'm going to save it as PDF file. I was trying to find the right word. Okay, saving as a PDF file. Post it. Still waiting for the PDF file to be created. So we have it. There you go. And now I can post the file. So I'm showing you exactly where to find it. And then this is where the video recording link will be posted. But the file, it's going to be content. We're going to go to chapter 3, lecture notes. These are my personal lecture notes. I'm going to call this lecture notes of video recording part 2 and 3. It is dated though as 331, 2026. There you have it. So you have both lecture notes for everything that is included in the video recording. Okay, I'm gonna go back to stop the recording.